Thank you. Hello everyone and welcome to Best Artifact session. Let me share my screen. Okay. So my name is Maciej Szpindler, and together with Massimo Torquati, we were sharing the artifact session track of the Europar. And before I will announce the authors of the best artifacts and their work, let me shortly introduce the idea of the artifacts and the approach we have applied for this conference. So the idea of artifacts is to allow authors to submit the additional material to their publication, to allow all the audience to reproduce the reported results. And it may be both source code and data and all other material that will help to reproduce the results that are described in the paper or in the work. But the most important thing is to supply also a documentation or a guide that will show how to exactly reproduce the results with a given codes or scripts or other programs that are part of the artifacts. And all the artifacts that are accepted is a formal part of the final publication. So there is a kind of tradition of the artifacts in the Europar conference series, and it's as an artifact that is attached to the submitted publication is not just another round of review, but it's rather a chance to provide high quality material and to improve, let's say, scientific impact of your work, and allow other researchers to easily, let's say, jump into to the context of your research. And our idea was to submit all the artifacts that was submitted. As you can see, roughly 1/3 of the submitted papers as well submitted their artifacts, and we have managed to accept almost all submitted artifacts. And we worked quite hard to help authors to provide a quality material as their artifacts. Some notices from the review process you may find interesting. So more than half of the submitted artifacts rely on the GPUs, which clearly shows the trend of our computing expectations. There was a range of approaches in terms of how this material was presented, starting from turbos with source codes and data, Git repos, and also containers. What I would like to say here is that on one hand, just raw code and data may be really complicated to reproduce the final results. But on the other hand, containers are really nice, and it provides much easier reproducibility. But on the other hand, it may create a black box when your source code is not easily accessible. So it may depend on your work which approach is the best. And again, documentation is a key factor to provide fine reproducibility. And for this reason, this year we have selected again a best artifact, and I would also like to announce that Szpindler sponsored award of 800 euros for the best artifact. And this year, best artifact is from Najeeb, Ahmad, Buse, Yilmaz, and Didem, Unat from Koç University, Turkey. And the artifact is for a work of a prediction framework for fast sparse triangular solves. And we've decided to nominate this work as best artifact as authors provide a clean and clear description and really high quality artifacts that are really easy to reproduce. But on the other hand, also the work itself is very interesting, while it combines, let's say, traditional numerical algebra problem together with machine learning approach, and I think it's a right moment to share the presentation of authors. May I ask for it?
Hi everyone, my name is Najeeb Ahmad. I am a PhD candidate in computer science and engineering at Koç University, Istanbul, Turkey. I'm a part of Koç University Parallel and Multi-Core Computing Lab, headed by my thesis advisor, Dr. Didem Unat. I welcome you all to my talk, in which I will share with you our research dealing with accelerating sparse triangular solve computations on heterogeneous CPU, GPU systems. My talk is divided into two parts. In the first part, I will talk about our machine learning based prediction framework for predicting the fastest sparse triangular solve algorithm on CPU GPU platforms. And in the second part, I will share with you our experience with artifact evaluation process at Europar. I will begin with the introduction of our research problem. Sparse triangular solve is an important computational kernel used in many scientific computing and other numerical applications. And in many cases, it is also the most time-consuming part of the application. For instance, in ILU preconditioned GMRS solvers, our empirical observation as well as results from previous research has shown this fact. Over the years, researchers have developed many algorithms for this kernel for both the CPUs and the GPUs. However, to date, there is no single algorithm or platform that has been shown to give fastest solution for all inputs. The reason is that, like many other sparse kernels, performance of this kernel depends on the input matrix sparsity pattern. Now, if we can somehow select the fastest algorithm for this kernel, it will boost application performance. However, making this decision is not a trivial task. One method is to run each algorithm for a given input and select the best one. But this process becomes tedious and time-consuming if there are many algorithms and many input matrices. To aid the programmer with this selection process, we propose a machine learning-based prediction framework that can predict the fastest sparse triangular solve algorithm for a given input. The framework has the ability to automatically train the prediction model with features and algorithm performance data for a diverse set of matrices. Also, the framework is extensible with new training datasets and algorithms. Performance evaluation of the framework on a state-of-the-art CPU-GPU machine finds it to give good prediction accuracy and SpTRSV speedups with acceptable prediction overhead. As auxiliary contribution, we analyze the performance of different SpTRSV algorithms on our evaluation platform. In addition, we identify some matrix sparsity features that in some ways determines SpTRSV algorithm performance and can be helpful for further research in this domain. Now some background for our work. So what is sparse triangular solve? As its name implies, it solves sparse triangular systems. These systems take the form Ly equals P or Ux equals Y, where L and U are lower and upper sparse triangular matrices respectively, and X, Y, and B are dense vectors. Because the nature and computational characteristics of the two triangular systems are similar, we will focus on the lower triangular systems in the subsequent discussions. In general, sparse triangular solve is an inherently sequential operation. This is because there exist interdependencies among different unknowns. These dependencies can be represented by a direct acyclic graph, as the one shown on the right for the matrix on the left. In this graph, the nodes represent unknowns and the edges represent dependencies among them. The nodes can be divided into groups called levels, such that the nodes within a level can be potentially computed in parallel. While computations on the nodes in level 0 can immediately begin, computation on higher levels can begin only once their dependencies from lower levels are resolved. This explains the sequential nature of this kernel. Because the number of levels and nodes within a level vary from input to input, performance of algorithms written for parallel or sequential performance varies from input to input. Other specific features such as row and column lengths affect algorithm performance also. This is why a single algorithm does not perform best for all inputs. There are two widely used classes of algorithms for exact solution of sparse triangular systems, namely level scheduling algorithms and synchronization-free algorithms. In level scheduling algorithms, there is a synchronization barrier between two levels. That is, computation on the higher level can begin only once computation on its preceding level have completed. In synchronization-free algorithms, there is no synchronization barrier between levels, and computation on a node can begin as soon as its dependencies are met. To test performance of some algorithms on a modern CPU-GPU machine, we choose 2 CPU and 4 GPU algorithms and compare SpTRSV winners for a set of matrices. As shown, there are at least a few winners for each of these algorithms, and over 1/3 of these winners are on the CPU. So when searching for the fastest SpTRSV algorithm, both CPU and GPU algorithms should be considered. Our research aims to answer the question of how to select this fastest algorithm on a CPU-GPU platform. To select this fastest algorithm, we propose a machine learning-based prediction framework that trains a prediction model on matrix features and performance data of a set of SpTRSV algorithms for a matrix dataset. This model can then be used to predict the fastest algorithm for any input matrix. The framework has 5 components: an automatically downloadable set of matrices, a matrix feature extractor for matrix sparsity feature extraction, a set of SpTRSV algorithms we wish to choose one from for our input, a performance data collector that collects performance data of each algorithm for an input matrix, and a model trainer and tester which uses matrix features and performance data for the sparse data set to train a prediction model that can predict the fastest algorithm. The framework is automated, extensible with new algorithms and datasets, and requires least user intervention for model training on a given machine. Feature selection is one of the most important parts in our framework design. It is only possible to achieve higher prediction accuracy if the features can capture performance characteristics of all algorithms we wish to choose from. Also, the feature set should be general enough, making extension of the framework with new algorithms possible. For the feature set selection, we only consider structural features as they can completely capture computational characteristics of SpTRSV algorithms. Initially, we started with 50 features and based on the feature scores and model cross-validation results, chose to keep the top 30 features for our model. The feature used by our prediction model include number of non-zeros and rows in the matrix, number of levels in the dependency graph, number of non-zero per level statistics, rows per level statistics, row and column length per level statistics, overall matrix row length statistics, and overall matrix column length statistics. In this table, the score rank column shows score rank for each feature. A smaller score rank means a higher contribution of that feature in the prediction. To efficiently extract these features, we have developed a matrix feature extractor that utilizes both the CPU and GPU for feature extraction. The performance data collector of our framework works by collecting performance data of all algorithms for an input matrix and reporting the ID of the fastest algorithm. Then, the model trainer and tester uses features and IDs of the winning algorithms for our dataset as input and target respectively and trains the prediction model. For model selection, training, testing, and evaluation, we use scikit-learn library in Python and use supervised machine learning for our prediction framework. We chose not to use deep learning for its larger data set and higher training times requirements, and because supervised learning is giving us sufficient prediction accuracy with acceptable prediction times. For the model selection, we evaluated a number of classifiers provided by scikit-learn library and chose random forest based on its high cross-validation scores. For model training and testing, we split our matrix dataset into 75% training and 25% testing sets, train the model with training set, and evaluate the model with a testing set using 10-fold cross-validation. In practice, sparse triangular solve is generally used as part of a bigger numerical application. Depending on which platform the rest of the numerical application runs, choice of fastest algorithm may be affected due to presence of inter-platform communication overheads. Consider the scenario where computations before SpTRSV run on CPU and after it on the GPU. In this case, if SpTRSV is on the CPU, there is one data transfer of the solution vector from CPU to the GPU. On the other hand, if SpTRSV is on the GPU, right-hand side B is to be transferred from CPU to GPU. Similar can be said for the case when computations before and after SpTRSV are on GPU and CPU respectively. In these scenarios, as the same amount of data is transferred between the two platforms, the data transfer do not impact SpTRSV algorithm selection. Now consider the cases when computations before and after SpTRSV are on the same platform. In this case, if SpTRSV is on the same platform as the rest of the application, no inter-platform data communication is incurred. On the other hand, if the SpTRSV is on a different platform than the rest of the numerical method, two vectors are communicated between CPU and the GPU. In this case, data transfer does impact algorithm selection, as data transfer may render a fastest algorithm slower than some other algorithm. The framework can account for these cases by taking these overheads and configurations into account. For evaluating the framework, we use a state-of-the-art machine with an Intel Gold CPU and NVIDIA V100 GPU. In software, we use Intel Parallel Studio for Intel MKL and host compiler and NVIDIA CUDA for the GPU. As our matrix dataset, we use 998 real square matrices from SuiteSparse Matrix Collection. Performance comparison of the 6 algorithms which I previously showed for a smaller dataset confirm again that there exist winners for each algorithm for this bigger dataset too. On the CPU, MKL sequential is the dominant algorithm, winning in most cases, while on the GPU, it is the sync-free algorithm which is fastest for most matrices. The winner distribution on the CPU-GPU shows the significant percentage of winners exist on both the platforms, once again confirming why considering both the CPU and GPU in search of fastest algorithm is important. This figure shows the box plots of cross-validation results for our prediction model. With the 30 features we have chosen, Mean framework accuracy is 87%, with values for the other parameters in the similar range. These plots also show a smaller spread of these metrics, which is an indicator of good model performance. We also investigated using a fewer number of features for our model. In the box plot on the right, model performance metrics with top 10 features based on their feature scores are plotted. We noticed that not only the mean values of the performance metrics drop, but the spread of the box plots also increase. Therefore, considering higher prediction accuracy, negligible extra overheads, and the extensibility of the framework, we chose to keep the original 30 features. This figure shows the speedups achieved by the framework versus when programmers stick to a single algorithm for all inputs. To explain these plots, let us consider the top left plot for MKL sequential algorithm, which shows the histogram of speedups achieved by the framework over MKL sequential for our matrix dataset. Each bin corresponds to speedups between two integer values, and each bar shows the number of matrices in that bin. The first bin shown in red shows the cases where speedup is less than 1. The mean represents harmonic mean. We notice that the mean speedups achieved by the framework over each of these algorithms range between 1.4 and as high as 2.7 for SuiteSparse V2 with no level scheduling. Also, for all the algorithms, in over 95% of the cases, framework achieves speedups of 1 or more. From these results, we conclude that the framework achieves significant speedups in most cases over arbitrary choice of the algorithm. To evaluate the framework overhead, we compare its mean overhead with that of an aggressive user who tests each algorithm to find the fastest one, and a lazy user who conservatively chooses an algorithm. For this analysis, we divide the matrices into three categories based on their sizes and separately consider the case where we include ILU factorization overhead shown in the top three figures and exclude it shown in the bottom figures. For the case without ILU factorization overhead and matrices less than 1 million rows, framework overhead is at par with aggressive user and more than the lazy user. For the matrices with more than 1 million rows, it is considerably less than the aggressive and sometimes less than the lazy user. For the cases without ILU factorization overhead, framework overhead is less than the aggressive user for all matrix sizes and less than the lazy user for matrix sizes greater than 1 million, except for sync-free algorithm. Given the speedups framework can achieve, these overheads are acceptable. In related research, we have OSCE library that can auto-tune SpTRSV on the CPU based on the statistical analysis of the input matrix and CPU characteristics. Languages and frameworks like Petabricks and Nitro allow algorithm selection for a kernel, but they are not specific to sparse triangular solve and need considerable programmer intervention. There exists an early work that chooses SpTRSV kernels between CPU and GPU, but uses heuristics and is limited to a specific application. A recent work more closely related with our research uses machine learning for SpTRSV algorithm selection on GPUs. However, it uses a fewer algorithms, is limited to GPUs, and shows lesser accuracy. In conclusion, our research contribution is a framework that uses supervised machine learning for predicting fastest SpTRSV algorithm on a CPU-GPU machine. Its prediction performance, speed-up gains, and acceptable overheads make it a useful tool that the researchers can use to accelerate their applications. Now I will switch to the second part of my talk, in which I will share our experience with getting the artifacts of our research evaluated. Artifacts are the support materials required to reproduce the claimed results of a research. Artifact evaluation process at Europar is completely optional but highly recommended. The artifact evaluation is carried out by a separate committee than the one that reviews the paper for acceptance. Our motivation for getting the artifacts evaluated was to make our research more accessible. Also, the process requires you to document your research, making it easier for you to refer to it in the future and in case you want to extend it. And last but not the least, it enhances the credibility of your research claims and gets you the artifact evaluated seal on your paper, which is very satisfying. Now I will show how the files in our artifacts are arranged and what they are for. In the main directory, we have folders for the sources, datasets, and the third-party tools. In sources folder, we place source codes for SpTRSV algorithm profiler and the matrix feature extractor. The dataset folder contains the dataset that we use for our results. The files in the dataset generator folder can be used to generate datasets on any machine. The third-party folder contains third-party tools that are used by our framework. These have been included in our framework to make it more self-contained. The files in the main directory include the overview document, which is a mandatory document to be included in the artifact, the dataset generation guide that researchers can refer to generate training datasets on any machine, a build script that builds all source codes with a single command line, and an evaluation script that can generate each figure, table, and statistic in the paper with a single command line. These files have been written keeping in view the ease of use of the artifact. In the overview document, before beginning the mandatory section, we include an artifact overview followed by the description of the artifact file structure. After that, we provide the first mandatory section of the overview document and give step-by-step instructions on how to install necessary software to reproduce results. The instructions also give estimated time to complete each step. Coming to the most important part of the document, in the step-by-step instructions to reproduce results, we provide details of our evaluation platform and single command line to reproduce results for each figure and table in our paper. For this purpose, evaluation script takes a single argument, that is the name of the figure or table to be reproduced, and reproduces the result. Like the getting started section, this section also gives estimated time to complete each step. In addition to the mandatory overview document, we provide a dataset generation guide to generate datasets for our framework on any CPU-GPU machine. It provides instructions on installation of tools and necessary steps to generate these datasets. In conclusion, artifact evaluation is a somewhat time-consuming but a highly rewarding process, and we are happy that we became part of this process for our research. In addition to the official artifact repository, we have created a mirror of the artifact, and we will be happy to take any suggestions and queries about our paper and the artifact. I thank you all for listening to my talk. I will be happy to answer any questions that you may have.
Thank you. Congratulations for the authors. And now we have time for questions. I see one question on our Slack channel.
Hello, can you hear me?
Yes.
Okay, thank you.
So the question is, how much efforts are required to further extend the framework to, and the question is, to other sparse matrix operations like sparse matrix multiplication, and extend it to the distributed memory systems?
Okay, first of all, I would like to thank the Europar committee to consider our artifact for the best artifact award and awarding it. It's indeed a real, it's a great matter of pride and honor for us. Coming to the question by Hatim, to extend it to other sparse matrix operation, I think yes, it is possible. Most of the things like automation in the framework is there, and as regards the other operation like sparse matrix multiplication, etc., we need to consider I think separate set of features. Probably we need to evaluate those. Other than that, and it, of course, considering other algorithms, we have to write ways to like profile those algorithms and write the codes to profile those things. Other than that, I think this can be easily extended to incorporate other algorithms. I hope this answers the question. Yeah, the second part about the distributed memory systems. So I'm not sure what exactly Hatim wants to ask in this case for distributed memory systems. Can you clarify your question, Hatim?
Hatim, you're mute. We can't hear you.
So giving chance to Hatim to ask the question again, I would like to ask another question. Could you please comment on the choice of the input matrices types? You meant 37 matrices. What was the let's say approach to select these matrices?
So for initial evaluation, we used 37 matrices, and we took these matrices from previous research papers. Though the paper being used by previous research papers for research on the sparse triangular systems. After that, when we move to the larger data set for the machine learning model training, we select those algorithms based on the criteria that they should be real and they should be square. So these were the criteria for selection of these matrices.
Okay, thank you. I see no further questions. I encourage everyone to ask questions later on Slack.
Just quickly following up on Najeeb, on the question that I asked about distributed memory system. You
Yes,
looked at system CPU plus GPUs, and I was wondering, in terms of effort and learning, your model, training your model on distributed memory system, how much, what does it require and how much effort is needed to do that?
So for that, I think first requirement is that we should consider those algorithms that can run, the implementations of the algorithm that can run on multiple machines. So first task is that. Another thing, the change will come that then we will need to take into account internode communication, which we are not taking into account in this work. It's only CPU, GPU communication. So if we have sufficient number of those algorithms and we take these factors into account, I think our framework is good to go for distributed memory systems as well.
Thank you.
You're welcome. Thank you for your questions.
Okay, thank you for attending this session. I'm afraid we are running out of time. So now we are switching to another session. So thank you again for attending.
Thank you everybody for your question and interest in the talk.
Yes, thank you for the session. Thank you, Maciej, for chairing, Najeeb, Tariq for presenting. So we will be starting the data management session in the same room in 1 minute. So Morris will take over here, and the second session will go in room B. So for accelerator computing, please switch to room B on Zoom and YouTube. The session is also starting right now. Thank you.